In this video, we're going to review the concepts from Chapter 1. The material in Chapter 1 was primarily covered in your ALEX pre-course that you did before the start of the semester. The majority of this material will not be covered on any of the exams in this course, but the material is essential for your understanding, and you'll use this material throughout the course. So let's get started. We're going to just have some basic definitions, and then we'll look at some quantitative concepts that are important. So our starting place is chemistry, and what is chemistry about? Well, chemistry's really got three key things associated with it. We're looking at matter, but what we're concerned about with matter are, first, its properties, second, its changes or transformations, and then third, the energy flow that's associated when transformations do occur. Now, a variety of scientists and engineers look at the properties of matter, and chemists do as well. One of the key areas for chemistry, and probably the most important area, is the changes or transformations that matter undergoes during a chemical reaction. So understanding chemical reactions and predicting transformations that will occur under various conditions, that's what chemistry is all about. Now, anytime we have a transformation, there's going to be an energy flow associated with that. So we need to understand some basic ideas associated with energy. So as you know, energy is the ability to do work, and energy can be broken down into two forms. One is potential energy, and the second is kinetic energy. And the sum of potential plus kinetic energy is the total energy for the system. Now, potential energy is the capability to do work, but it's generally stored energy, or it's often associated with the position of an object, the position or the state of an object. The kinetic energy is associated with movement of an object. Now, we can nail this down a little more tightly for chemistry. In chemistry, potential energy is associated with chemical composition. So, for example, sodium chloride will have a different potential energy content than will sodium bromide. Potential energy is related to the chemical composition of a system. The kinetic energy of a system is associated with its temperature. And we'll find out later that the temperature is associated with atomic and molecular motions or speeds. Now, we're going to spend quite a bit of time on energy when we get to Chapter 6, because we're going to look at potential and kinetic energy and how they transform in chemical reactions. We'll see that virtually all chemical reactions involve a change in potential energy. Scientific problems are generally approached with the scientific method. A little more broadly, the scientific method is just generally a good way to think about the universe. It's a way for you to think about how you're going to fix your car, or how you might solve a problem. It's a very powerful approach. And this approach is laid out here in a series of 5 steps. The basic idea behind the scientific method is that we first make some observations. And we make these observations, and we try and get some sort of insight into why these observations are occurring. We develop what we call a hypothesis. A hypothesis is some proposal that might explain why something occurs the way it does. So that's why in many cases, chemistry is a hypothesis-driven science. Now, the next step is probably the most important, because we can always develop hypotheses or ideas and proposals to explain something, but the most important part is to do an experiment to test our hypothesis. Any useful hypothesis has to be disprovable. So we have a saying, theory guides, experiment decides. And so we have a hypothesis or an idea, but then we try and come up with a good experiment that will really test or challenge our hypothesis. Now, if we make these observations and they're consistent with the hypothesis, Then we go on to develop a model to explain what we've observed and what our experiment has told us. Now, an important thing to understand is that simply because a model matches reality or our observed experiment doesn't make the model true. In fact, at some level, all models are wrong, but that's okay. Hopefully, we make good experimental measurements that are reliable and are reproducible. Those become the facts with which we work, and then we develop models that will not only explain our experiment, but more broadly explain observations throughout nature. Now, once we have a model, of course, our real goal as scientists is to break down the models we have, and that is to come up with a more detailed experiment that will ultimately break our models so that we can come up with new and better models. We're always looking to improve our models, and we want to challenge our models with more advanced experiments. When we move on to the mechanics videos later, we'll go through an example of the scientific method for something with which you'll be familiar. Now, there are some engineers in the course, and the engineers use something that's very similar to the scientific method. It's called the engineering design process. It turns out that most chemists actually use this approach in their research because chemists are usually solving scientific, engineering, and technological problems. And in fact, since we have a lot of very solid paradigms within chemistry, we're now trying to apply those paradigms, those tools that we have to solve problems in medicine, in engineering, in information science, and other areas. The basic flow of the engineering design process, rather than starting with a simple observation in nature, you have a problem that you want to solve. Maybe you want to detect a particular antibody in blood. So you define your problem, you do some research to come up with a solution to your problem. You specify the precision, limits of detection, all the requirements for your problem, and you come up with a solution to do this. So now the first four steps are really taking your problem and coming up with a solution to it. This is equivalent to the hypothesis stage in the scientific method. Next, you develop a prototype to solve your problem. So you developed a prototype, and then you test that prototype out. So this is equivalent to the experiment part. If the prototype works, then you're in good shape. You've met your requirements and you communicate results, and then you go on to maybe a more difficult or more different problem. If your solution, your proposed prototype solution does not work, then you need to iterate and come up with a design change and improve your prototype to be able to solve your problems. Now, whether you're using the scientific method or the engineering design process, in all the cases that we're going to look at this semester, we're going to be looking at measurements and observations that are quantifiable. And anything that's quantifiable has to be related to a standard system. So really, any good measurement or any good scientific observation should have a numerical value associated with it. But that numerical value won't mean anything unless it's tied to a standard. And those standards are what we call units. Now, it turns out that there are 7 what we call base units. So you can see in this slide, we have the SI, that's the International System base units. And the base units are mass, length, time, temperature, electric current, amount of substance, and luminous intensity. With simply these 7 units, or combinations thereof, we can describe every observable that we know in the universe. Now, the reason these 7 units were chosen were not that they were necessarily unique. You can imagine, for example, rather than electric current in amperes, we could have chosen electric charge in coulombs. But the reason amperes were chosen is that they can be measured more easily and more precisely. These 7 units were chosen because of the ability that we have as scientists to precisely measure them, and that they're all based on fundamental properties of the universe. So that's a kind of a very profound philosophical thought, in a sense that you can describe pretty much every physical scientific observable with just these 7 units or their combinations. So all scientific observables may be described or derived from only these 7 units. They were chosen because they're readily measurable at precise levels. Now, combinations of these 7 units are what we call derived units. So if we go up a slide, these are our base units. These are, in some sense, the special units, the foundation upon which we work. And then all the other things that you might want to measure. Speed. So for example, speed is length divided by time, or distance over time. That's a derived unit. Volume is an important unit. So that would be length cubed. Area would be length squared. Density is mass divided by length cubed. Molar mass, which we'll spend a lot of time working with this semester, is amount of substance divided by mass. So we can come up with, you can think of a variety of different properties, and if you think of that property, you think, what unit would you use? If it's not one of those 7 units, it'll be some mathematical combination of those 7 units. Next, it's important to recognize what we call the digital or decimal prefixes that are used with our unit systems. And typically, as human beings, we like to work with numbers that are near 1. So anything from about 1/10 to about 10, we like to work with those in that numerical value, in range. That's something that's easy to understand. And so often we can have a number that may be very large or very small, and we want to use those unit systems, but it may be very, like for example, we might have something that is a very large number of those units. So for example, 10,000 meters would be, that's a very large number. So what we can do is we can use a prefix in front of the unit system. So for example, for 1,000, we'd use kilo. So we would have a kilometer. That'll be 1,000 meters. So 10,000 meters would be 10 kilometers. And you can see there's a whole series of these here. You don't need to memorize all these, but the ones in bold are ones with which you should have some familiarity, because you'll see these throughout the semester. And in fact, as you move on in your scientific careers, you will find that these prefixes are used all over the place. And so you should be comfortable with what they are. It's always nice to have these right in your memory, so that way you don't have to go look something up or spend too much time thinking about something trivial like the prefix on a unit. So mega would be 1,000,000. So mega is obviously something big. So if you had a mega buck, you'd have $1,000,000. Mega dollar would be $1,000,000, or a megaton would be 1,000,000 tons. Kilo is 1,000. Deci is used somewhat frequently. It's probably the least frequently used on this list of bolded. That's 1/10. Centi is 100th. That'll be very important. So for example, a centimeter would be 1/100th of a meter. That's a little less than 1/2 of an inch. You may be familiar with that. Milli is 1,000th. Micro is 1,000,000th. Nano is very important. So a nanometer is 1/1000th of a meter. And pico is 1/1000000000th. So you should know the prefixes in bold, and you should know what the prefix symbol would be. So mega is big M, milli is small m, micro is Greek letter mu. And then you should know the associated numerical value for that. So the conventional notation or exponential notation, whichever one you're more comfortable remembering. Now, when we make measurements, every measurement has some uncertainty associated with it. If you measure a number, you're really estimating that value to a certain level of precision. You may have a very high level of confidence at a certain level, but beyond there, your knowledge becomes unknown or uncertain. So when we write down a number, we need to be very careful when we handle numbers. We need to only convey the information that we know to be true, and any uncertainty we have needs to be articulated clearly. And numbers that we don't know, we need to eliminate because we don't want to imply that we know something that we don't. And typically, the rightmost digit of any quantity is the least certain digit, and it's often estimated. It says here always estimated, and you'll see that in your textbook, but let's just say it is often estimated. You cannot make the statement that it's always estimated. The recorded digits, both certain and uncertain, and so uncertain simply means the last digit that you have estimated. Those are the significant figures. The ones outside, the ones that you know, or the last one that you might estimate, those are valueless digits, and if they're not placeholders, they need to be eliminated from the number. The more significant figures in a quantity, the greater its certainty, or you could also say the higher its level of precision, the more precise that you know a quantity. So let's take a simple example to look at. This is a case with two thermometers. The one on the left has a higher precision. The one on the right has a lower precision. The one on the left will have more significant figures in the reported number. The one on the right will have fewer significant figures in the reported number. So you can see that this is a thermometer that's measuring temperature in Celsius. It's a little bit above room temperature, so it's you can see that it's between 32 and 33. And if you look closely, it's 32.3. It's right next to the 10th place, that 0.3 there. And then if you look at it, you're closer to the 32.3 than you are the 32.4. Look closely, you're closer to 32.3 than 32.4. In this case, we might estimate, and your text has indicated they estimated as 32.33. You might estimate as 32.32 or 32.34, but that lets you know that that last hundredths of a place is estimated. Now you might ask, why do I put that number in if I don't know it? Well, it tells you something. It tells you that you're closer to 32.3 than you are to 32.4, but you're not really super close to 32.3. So it gives you it contains some information, but it's really an unreliable number for high-low precision. So you might write 32.33 plus or minus 0.2 or 0.02 to indicate that 0.03 could vary anywhere from 0.01 up to 0.05. It's in that range. Now on the right-hand side, you can see that we have marks at 20, and then every degree up to 30, and every degree up to 40. And so at 30, we can see we're at 31, 32. So the top of the mercury meniscus is close to 32. And in this case, if you look closely, your text has guessed that it's 32.3. That tells you that you feel pretty strongly about 3 and the 2, but the 0.3 is more uncertain. Now, when you see a number, or when you write a number down, we need to recognize what are the significant digits, because oftentimes you'll see lots of numbers, but only certain ones will contain good information. So if someone has correctly written down their experimental values and properly propagated the number through, when you have your final answer, all the digits that are represented are significant, except the zeros that are used only to hold the other numerical values at their right location relative to the decimal point. So you want to make sure that the measured quantity has a decimal point. Now there are some cases where it won't, and so we'll look at how we deal with those in a little bit. You typically start at your left, you move to the right until you reach the first non-zero digit. And then we count that digit, and every digit to its right is significant. In the next video, after this video, we're going to do some examples with this. So we'll illustrate this. But we've got we'll have some examples here in a minute. So now typically zeros that end a number are significant unless they're just a placeholder and there's no decimal place. So let's look at an example, 1.030. That number, it has 4 significant figures. And you say, well, what about the rightmost 0? Well, that must contain information. That must be 0 rather than 1, because if it did not contain any information, we wouldn't put it there. We would simply have 1.03. But by writing 1.030, we're implying that that last 0 is not another value. It's not 1 or 9 or something else. 1.030. All 4 of those contain information. Those are all significant figures. The next number, 5,300 decimal place, liters. That has 4 significant figures. The zeros are followed by a decimal point, and that decimal point implies that everything to the left of the decimal place has precision. If there isn't a decimal place, and so for example, if you see a number 5300 with no decimal place, 5,300 liters, there's only 2 significant figures. So then the question is, how do I write 5,300 with 3 significant figures? That's when you need to use scientific notation. You'd write 5.30 times 10 to the third. Now, oftentimes we're going to make multiple measurements, and then we will combine those measurements in a mathematical operation to deduce the final value that we want to get at. So for example, you might have a measurement of distance that's estimated or measured, and a time that was estimated or measured with some device. And if I wanted to calculate my speed, I would take my measured distance divided by my measured time. But each of those numbers may have a different number of significant figures. So how many significant figures will there be in my final answer? Well, it turns out that there's just a couple of simple rules. The first one, for multiplication and division. Anytime that you take 2 different numbers and you either multiply them or divide them, your final answer has the same number of significant figures as the operated number that had the fewest significant figures. So, for example, if you take 9.2 centimeters times 6.8 centimeters times 0.3744 centimeters, you multiply that out, you'll get cubic centimeters, which is a volume. 9.2 has 2 significant figures. 6.8 has 2 significant figures. 0.3744 has 4 significant figures. You multiply them out on a calculator, you get 23.4225. But some of those numbers have no information content. The rightmost 5, that's really a random number and does not tell you anything. The 2 next to the 5 does not. And the following 2, that doesn't either. It turns out that the answer only has 2 significant figures. The correct answer is 23 cubic centimeters. Now, if we add or subtract 2 numbers, we treat things differently. It turns out that the answer has the same number of decimal places as there are in the measurement with the fewest decimal places. And so what we do is we look at placeholders in this case. So the least precise placeholder determines the least precise placeholder in our answer. So, for example, if we add 2 volumes, 83.5 and 23.28, We add these together, we get 106.78. But we notice that 83.5 is only precise to the 10th decimal place. So our answer is precise to the 10th decimal place. So in this case, 83.5 has 3 significant figures, 23.28 has 4 significant figures. Our answer is 106.8. That happens to have 4 significant figures. But I'm going to throw out another example. We won't write this one down. If you have 83.5 and you add 23.2, your answer would be 106.7. So each of your numbers that you're adding would have 3 significant figures, but your final answer would have 4 significant figures. Doing a subtraction, if we take 865.9 and we subtract off 2.8121, subtraction is just addition with a negative sign on it, right? So 865.9 has only precision to the tenths of a decimal place. Therefore, our answer, 863.0879, must truncate or stop at the tenths decimal place. So our answer is 863.1. Now you'll notice we've done rounding, and this is just a reminder. We assume that you know how to do rounding. If not, then you'll do this. You'll have had practice to do this in ALEKS. But the final digit that you remove, the one that is less certain than your least certain digit that you're going to write in your answer, if that digit is either 5, 6, 7, 8, or 9, the top 5 numbers, then your most uncertain digit in your reported answer is increased by 1. If the digit removed is the first 5 numbers, 0, 1, 2, 3, or 4, you don't change the last digit. That's the rule to follow for rounding, and that is the correct way to approach it. Now there's one special rule to remember. Exact numbers have no uncertainty associated with them. So let's say that we have a graduate course this semester where there are 12 students in the class. So 12 is the number 1, 2. What is the number of significant figures? Well, it turns out that 12 is an exact number. So we can't have 12.1 people. We can't have 11.9 people. We can't have a half or a fractional person. Every person is an exact value. So you could think of it as 12.000 with an infinite number of zeros, or you could say it's an integer, and integers have exact precision associated with them, so they do not limit the significant figures in your calculation. That's the conclusion of the concepts for Chapter 1. Next, you'll go on to some basic mechanics on Chapter